Hi everybody, welcome to Scientific Method Quiz for Explanation. Just like in the other scientific method units, this quiz will follow the same format. The first 5 questions will be based on an experiment that you've either done or seen, and the last 5 questions will be more general, based around this area of scientific method. So let's have a look together. The students at Charles George School are investigating the effect of height on energy transfer. The students build ramps of different heights using textbooks. The students take a car and roll it down the ramp. They measure the distance that the car travels each time. Before starting, they research about potential energy and kinetic energy on the internet. They find that the higher the starting position, the more potential energy the object has. So they are looking at height based on kinetic energy. So we're looking at textbooks. We can have one textbook and then a ramp coming down from the one textbook. We could have 2 textbooks and a ramp coming down. We could have 3 textbooks and a ramp coming down. What changes each time? Well, we're changing the height. Each time, the height is increasing. And what the students found was that if the starting position is higher, there is more potential energy. And what happens to potential energy? Well, when the object moves, the potential energy becomes kinetic energy. So what would be an appropriate hypothesis? Remember, a hypothesis is a guess, a prediction about what will happen. A, the height of the ramp will have an effect upon the distance the car will travel. Now, an effect is not really a prediction. If it said the higher the ramp, the further the car will travel, that's a prediction. You're guessing that if you increase the size of the ramp, you will increase the distance that the car will travel. But A is too broad. It's not really predicting what will happen. We don't know if it will go further or less far. B, the higher the ramp, the more potential energy the car will have. So the further it will travel after it leaves the ramp. That makes sense. If the ramp is higher, then the car starting has more potential energy. So when it gets to the end of the ramp, it will travel further. B looks like a good one. C, energy cannot be created or destroyed, so each car will travel an equal distance. Well, the problem with that is the first part is true. Energy cannot be created or destroyed. But the problem is with the second part, where it's saying the cars will travel an equal distance. The passage said higher objects have more potential energy. So if they have more energy, then they have more energy that they can use. So they will probably not go an equal distance because more energy would mean more movement. So C looks like it's also going to be wrong. And then the last one, the car released from the shortest ramp will travel the farthest distance. The short ramp, this one here, will have the biggest distance. Well, the short ramp will have less potential energy. So less energy can become kinetic energy. Therefore, it will travel less distance. So I think D is the opposite. B is what we would expect to happen. Now, for the second question, we're asked to identify the independent and the dependent variables. We have the weight of the car, the height of the ramp, the distance traveled, and the material of the ramp surface. Well, remember, independent is something that the person doing the experiment is choosing, something they are changing, something that will be different. Well, we see the word different in the passage. It said the students build ramps of different heights. using textbooks. So the thing that is different each time is the height of the ramp. So height of the ramp is going to be the independent variable. The dependent variable is something that changes because of the independent variable. If you like, the independent variable is the cause and the dependent variable is the effect. The effect is something that we can see, that we can observe, or that we can measure. And we see the word measure in the passage. It says they measure the distance that the car travels. So the distance that the car travels must be the dependent variable because that's what they are measuring. Which of the following is not a potential source of error in the conduct of the experiment? Not a source of error. So A, the students used different thickness of textbooks for each ramp because they couldn't get enough of the same. Well, if we have one thin textbook and then we have one thick textbook, this could be a problem. Two thin textbooks will be very different to two thick textbooks. So they should really try to use the same textbook to remove something that would be changed. Anything that can be changed is a variable, and we only want to have an independent variable and a dependent variable based on that. Changing the thickness of the textbook would add an extra difference that would not be helpful for the experiment. So that is a potential source of error. We're looking for something that is not a potential source of error. B, the student conducted the test at each height 3 times and calculated the average. This is not a source of error. This is very good. When we're designing experiments, if we want to increase the accuracy of the results, then we should repeat the investigation. If we're measuring and we calculate an average, that will reduce errors due to the experimenter. Sometimes, for example, if you're letting go of the car, you might not start the watch at exactly the right time, or you might give a slightly different force to the car each time. So these are human errors, experimenter errors. By repeating the experiment and calculating an average, you are getting a more accurate result. So this is not a potential source of error. We're looking for what is not an error, not an error. See? Each student used 3 different cars, so they didn't need to collect the car after each trial. But that would be a source of error. Each car could have different size wheels. Different size wheels will create different friction. They could be different weights, which might affect the acceleration. There would be lots of variables with different cars, which could impact the results of the experiment. So this is an error. That's why we don't choose answer C. And then D, on the lower heights, the car didn't move, so the student pushed it to start the movement, but only on the lower height did the student push. That's not good. So on the lower height, the student pushed, the student gave it extra energy. On the other heights, the student did not push, so they did not get any extra energy. That's an additional difference. We don't want to add more differences, so we do not choose D. Now calculate the average for each height. What is the difference? Now, first step, calculate the average, but then the question says, what is the difference between the average distance of the height which produced the greatest and the least distance traveled? So which one had the longest distance? Which one had the shortest distance? And what is the difference between them? So first step is to calculate the average for each height. So we have a column at the end. If we calculate the average by adding together and dividing by 3. So I've calculated the average for each of the heights for 1 textbook, 2, 3, 4, and 5. So that's the first step done. Then we say, what is the difference? So the difference means to subtract. subtract the greatest and the least difference traveled. So the greatest and the least average distance traveled. Well, the average is here and the distance traveled. Now you might think that one textbook would give you the least, but one textbook is 12.67. If we look on the line below, we have 11.37. So the least distance traveled was from 2 textbooks. So we need to subtract 11.37. The greatest distance traveled was 141. So we have 141 minus 11.37, which gives 129.63. If you got this wrong, you might have assumed that the least would be on line 1. But think about the previous question. When you do the experiment, you could make mistakes. You could be doing things that would impact the experiment, and that would impact the results. For example, if we look at trial 3 for one textbook, we get 14.3, and that's higher than anything else for either one textbook or 2 textbooks. So maybe the person doing the experiment hit the car at the top of the ramp and gave it extra energy so it traveled further distance. If that happened, then that would cause an error in the experiment. This would be an outlying result. We would call it an outlier. And when we have an outlier, sometimes we even remove it from the experiment and just focus on those that are not outliers. So we could actually have calculated the average of just 11.2 and 12.5, which would have given an average of 11.85. And 11.85 is still bigger than 11.37. So even if you remove the outlier, you would still have an average that was bigger than the 2 textbooks. So there's probably been a few errors in this experiment. Maybe the car wasn't moving, so with one textbook, the students doing the experiment hit the car, but that caused an error because the car was getting extra energy. Anyway, this type of question, you go carefully, calculate the average. If you see the difference, you need to subtract, and need to make sure that you choose the right numbers for subtract, and you must make sure that you give it in the correct format, 2 decimal places, so 2 numbers after the decimal point. After analysing the results, the students in this group find that the results do not confirm their hypothesis. Do not confirm. Why don't they confirm? Well, they said the taller the ramp, the further the car will go. But the lowest ramp did not go the shortest distance. The car on one textbook went further than the car on 2 textbooks. So what should they do next? Should they alter the data so that the results match the hypothesis? No. No. You never alter the data. The data that you have is the data that you must use. So you could think that there's been an error. You could start to review what you did, but we'll come on to that in a moment. You never change the data. You could reject the hypothesis and give up, but you might believe that the hypothesis was right. Rejecting the hypothesis is too quick. We need to understand why we got the results that we got. Either there was some scientific theory that we didn't think about, or there was an error in the experimental method. So it's too soon to reject the hypothesis, so not answer B. C, examine the experimental design for sources of error and then repeat the experiment. That would be good. Looking for sources of error and trying to correct them would be good. For example, making sure all the textbooks are the same thickness. Making sure that all of the cars are released and none of them are pushed. These things would improve the accuracy of the experiment. So if you get results that do not match your hypothesis, look at the experiment design, find the sources of error, remove them, and then try to repeat. That would be a very good next step. D, look for alternative results on the internet to replace the data. Well, this is very similar to answer A. It's about changing the data. It's about changing the numbers. You can't change it. You can't make it up. You cannot replace it with somebody else's data. The experiment that you did is the experiment that you did. The numbers that you got, you have to use. If the numbers that you got do not match what you expected, then you need to try to find a reason why, not just change it or replace it. On to another experiment. In this, a student wants to observe the properties of solutions with various amounts of saturation. She uses a common photograph developing chemical, sodium hydrosulfate, as the solute and water as the solvent. So iteration 1 just means first time. Iteration means the time, so the first time. A test tube is filled with 2 milliliters of water and 1 gram of hydrosulfate crystals. Second time, there are 2 grams added to 2 milliliters. So the 2 milliliters stays the same, but the grams doubles. And the third time, there are 3 grams and there are 4 milliliters. So they are both increasing this time. Both the solute and the solvent are increasing. In iteration 4, there are 30 grams and 2 milliliters. Well, 2 milliliters is the same as here, but 30 grams is a huge increase. We've dealt with 2 and 3 grams so far, but suddenly we're going to have 30 grams. That's a big jump. We don't like to have big jumps like that in science. So there might be a problem with iteration 4. Iteration 1, after they were mixed together, the test tube was shaken to dissolve the crystals. The crystals dissolve rapidly and the solution is clear. In iteration 2, there were several methods of shaking the test tube and then the crystals dissolve, so the solution was cloudy. In number 3, it was shaken and the crystals dissolved and the test tube became clear. In number 4, the test tube was placed in cold water until it returned to, it was heated first and then it was put into cold water and then it was observed that the particles were there but the solution was clear. So iteration 4 is just very different. In iteration 4, we have heat that is not seen in any of the others. There are 30 grams, which is much more than the others. And it was placed into cold water. So iteration 4 is not a good part of the experiment because it changes many things. But the question, as experiment 1, 3, and 4 all produced a clear substance, the student concludes that all 4 of the conditions were able to produce a solution, but there had been an error in experiment 2. Why might this conclusion not be accurate? She's thinking that experiment 2 has an error because there is a cloudy solution. Well, experiment 2 did eventually produce a cloudy solution, so there was no experimenter bias. That cloudy solution is a description. No experimenter bias is not supported. Why? Why can we say there was no experimenter bias and no experimenter error? B, experiment 4 was conducted under different conditions, so the results are not comparable to the other iterations. Well, it is saying 4, and the conclusion is that all 4 of the conditions can produce a solution. Because 4 is so different, it should not be compared to any of the others. And then C, solutions must be clear, so the crystals in the final iteration disprove the conclusion. Well, it is clear with crystals, but we do have a clear solution. And then D, the third iteration increased the solute by 50% and doubled the water volume. This is a description. It does not tell us why it was good or why it was bad. So it's not going to be D and it's not going to be A. What is happening in C? Why do we have crystal particles observed and a clear solution? Well, it might suggest that some of the crystals were dissolved and some of the crystals were simply not dissolved. So there is a solution, but it has become saturated, so not all of the crystals can be dissolved. Which of the following would not improve the experimental design? A, repeating the test at each iteration and calculating the average. This would be very good. We're not told how many times the student does it at each iteration, but always repeating and calculating an average is going to be good for increasing the accuracy. But we're asked what would not improve. B, using a stopwatch to record accurate time for dissolving of the hypersulfate. That would be helpful if we knew how long, if we used a stopwatch, because what does it say at the moment? It says at the moment until it returns, we don't know how long it took. It says dissolve rapidly. We don't know what is rapid. Is rapid 1 second, 2 seconds, 30 seconds? We don't know. And we have several methods of shaking. We don't know how long. So using a stopwatch would improve this experiment. C, increasing the number of iterations with different ratios of hyposulfate and water, having more ratios. So we have 2 to 1, we have 2 to 2, we have 3 to 4. If we increase the number of ratios, we could have 4 to 5, we could have 5 to 6. If we had different ratios, we could try to find out what the saturation point was. So if we had a greater variety of ratios of solute to solvent, then we could try to find out what the saturation point is. That would improve it. D, heating the solution in iteration 3 the same as iteration 4, that would not be good. That would not be good because iteration 4 is the part of the experiment that is not useful right now. Because iteration 4 was so different to everything else, we don't want to add the extra variable. We don't want to add heat as well as different proportion of solvent and solute. So either we're going to test the ratio of the solute to the solvent, or we're going to test the heat. We cannot test both at the same time. So D would be adding in extra change, and we want to remove changes, not add extra changes. Now decide if each of the following is the independent variable, the dependent variable, or something that could be controlled. The speed of the shaking. Well, this should be controlled. All of them should be shaken at the same speed. Otherwise, we don't know what is causing the speed of the reaction. Is it the shaking or is it the amount of solute and solvent? The amount of hypersulfate, well, 1 gram, 2 grams, 3 grams, 30 grams. This is what the student is choosing. The student chooses it, so it is the independent. And then the time taken to dissolve the hypersulfate, the time taken is what should be measured. So that should be the dependent variable. The temperature of the water should be the same every time. Only this one is heated. The other three do keep the temperature the same. We should always be keeping other things the same. This is an extra variable, so it should be controlled. It should be the same. And then the volume of water, well, actually, this is one of those experiments where there are two independent variables. There are 2 milliliters of water. There are 4 milliliters of water. So the student is choosing how much, because she's looking at the ratio of the solute and the solvent, and what ratio creates saturation. Therefore, the volume of water is a second independent variable. Normally, we only have one independent variable, but occasionally, two things can be changed. Another example where two things are changed is when you're growing seeds. If you change the amount of water and you change the amount of sunlight, well, this is an example where you have two independent variables. In a lab experiment designed to test the rate at which plants grow under artificial light, the kind of light used is which type of variable. So what are we looking at? We have an experiment to test the rate that plants grow. The rate, the speed, can be measured. This would be the dependent variable. What is changed? The type of artificial light. So the artificial light would be the independent variable. You can use different types of fake light to get different results. A student hypothesizes that eating a teaspoon of raw honey will prevent sneezing. So she thinks that if they eat a teaspoon of raw honey, there will be no sneezing in people who are allergic to pollen. So she runs an experiment to test her hypothesis. What would be the dependent variable? Well, sneezing would depend on, in her prediction, eating honey or not eating honey. So some people would eat honey, some people would not eat honey. What she will then do is she will count how many times the people sneeze. So the sneezing will be the dependent variable. Do they sneeze, yes or no? How many times do they sneeze? What she changes is if she allows them to eat honey or she does not allow them to eat honey. Okay. When it says will prevent, it means will change. So this will change or will affect this. Think about cause and effect, and that would help you to find the independent and the dependent variable. Well, that's the end of this video. Hopefully that's been helpful. There'll be another lesson on the scientific method uploaded to Moodle very soon. Hasta la,